Welcome. The second part of section 6 deals with the composition of functions. I apologize for my voice. Sorry, I'm sick. Actually, it probably sounds better than my normal voice does on video recording since it's about an octave lower. So let's roll with this here. What is the composition of functions? Composition of functions, basically I'm looking at taking one function and I'm inputting that into another function. So there's kind of two different notations that you'll see. One of them is this open circle. So big idea here, this doesn't mean multiply. If you see the open circle, this is actually read g of f of x. Or if I see the parentheses, this also means g of f of x. And both of these mean to first plug x into function f, then plug that result into function g. Also a note on the bottom, if both of these are functions, then the composite function, which would be what we're looking at here, if I plug one into the other, the result of a composite function will also be a function if the original two are functions. All right, so back to the idea of kind of a function machine. Remember, for a function, each input has one output. So if I have if I'm looking at a composite function, something like this right here, this is saying g of f of negative 4. So you want to start at the innermost parentheses. What I'm asking you to do on this problem is take negative 4 and first plug that into function f. So here's function f. If I take f of 4, f of negative 4, f of negative 4, anywhere I see an x, I need to plug in negative 4. F of negative 4 would be negative 4 squared, which is just 16. So if I think of the machine here, I'm plugging negative 4 into function f, I'm squaring negative 4, what should come out is 16. Then that output I'm going to plug into function g. So I've taken f of negative 4, f of negative 4 is 16. So if I want g of f of negative 4, really I'm looking at taking g of, f of negative 4 is 16. So now I want g of 16. So I'm plugging 16 into function g. And that would be, okay, here's my function g, so 3 times 16 plus 5, or 48 plus 5, and I should get out 53. So in the end, g of f of negative 4 is actually 53. First I input negative 4 into function f. Whatever comes out, I input that into function g, and I end up with 53. So why don't you look at these two functions? Actually it's the same functions, but let's do the reverse. So I have f of g of negative 4. So pause the video and see what you can come up with. First thing you should do is, if I look at the innermost parentheses, I want to plug in negative 4 into function g. So I'm inputting negative 4 into function g. Wherever I see an x, I'm going to replace it with a negative 4. So g of negative 4 should be 3 times negative 4 plus 5, or negative 12 plus 5, which ends up giving me negative 7. So g of negative 4 is negative 7. And then, I want to take f of g of negative 4. So now, I'm looking back to my original. Now if I have f of, g of negative 4 is negative 7. So I'm going to replace this g of negative 4 with negative 7, since that's what g of negative 4 equals. And then f of negative 7, now I want to use function f. So negative 7 squared. So here we go, I plug in negative 7 for x, and I square it, and I should end up with 49. So in the end, f of g of negative 4 is actually 49. Now let's look at this example. This is similar to what we just did, but now I'm asking for h of g of x. So instead of actually inputting a specific numerical value, I just want to keep this function in general. So I'm looking at the composite function. I'm combining function h of x and function g of x. So again, I guess I want to just start on the innermost parentheses. So if I plug x into function g, well, g of x actually equals this stuff. So if I see h of g of x, well, this is actually the same as saying h of, well, what is g of x? Well, g of x is x squared plus 1. So I want h of x squared plus 1. Well, if I understand what this function notation means, whatever I see in parentheses, I need to input right here in the function h. So if I want to take h of x squared plus 1, I want to input this whole thing wherever I see the x back in the original function. So h of x squared plus 1 would actually equal 2 times x squared plus 1 minus 3. So I'm just replacing x with that x squared plus 1. You could also think of it this way. I'm starting with this function, so g of x, and I'm going to plug this in right here. Essentially, I'm just substituting that value in for wherever I see the x in function h. And then certainly I can clean this up a little bit. So if I distribute, you get 2x squared plus 2 minus 3. So in the end, h of g of x actually is equivalent to 2x squared minus 1. And if you note my original functions, this is a parabola, this is a line. If I combine these, the composite h of g of x is also going to be a function. So now, why don't you attempt this? So we're going to do the reverse. Find g of h of x. And remember this notation with the open circle? So I got the open circle. That means the same as if I said g of h of x. Same question. So pause the video and let's see what you come up with. So now I'm actually starting with h of x because that's on the innermost parentheses. And I want to plug this into function g. So wherever I see an x, I'm going to replace that with 2x minus 3. Or you could think of it this way. This is like g of, okay, well, what's h of x? Well, h of x is actually 2x minus 3. So now let's go back to function g. Okay, anywhere I see what's in parentheses, I need to plug in this case, 2x minus 3. So I have 2x minus 3. I'm going to square all of that stuff and add 1. Now, careful here, people. If I'm taking 2x minus 3 squared, well, this is the same as 2x minus 3 times itself. I cannot just distribute that exponent in because I am adding these terms. So you're going to have to end up doing some foiling here. And if you go through and FOIL, you should have 4x squared minus 6x. Minus 6x would give you negative 12x. Negative 3 times negative 3 is 9. So I FOILed and kind of added those outside and inside terms at the same time. So in the end, g of h of x should actually equal 4x squared minus 3x plus 1. So this is my composite function. Oh, excuse me. Sorry. It might help if I if I combined my like terms correctly. Okay, so sorry. Negative 12x plus 10. Does that look a little better, hopefully? Now, let's expand on our domain talk from yesterday. If I've got something like this, this isn't a problem. My domain would be anything. So negative infinity to infinity. So the original functions of parabola, I can plug in anything for x. This is a line. I can plug in anything for x. So my original functions, parabola, line, when I combine them, I actually end up getting another quadratic function. which is a polynomial. I can certainly plug in anything for x. I don't have any domain problems. However, we do run into some problems, again, if I have like a square root function or if I'm dividing with functions. So when finding the domain of a composition of functions, here's some questions to ask yourself. Is the domain of the first function restricted? So that function that I see on the innermost parentheses, is there anything I can't plug in for x originally? Now, since the range of the first function is inputted into the domain of the second function, so whatever comes out of the first function is inputted into the second function, I need to ask myself, can all the numbers in that range be inputted as numbers in the domain of the second function? So let's take a look at an example to kind of expand what we were just talking about. So what is the domain of r of t? So if I want to look at a function r of t of x, so the composite, I'm starting with function t, and I want to plug that into function r. So first thing I'm going to look at is, well, this original function that I'm starting with. Is there anything that I can't plug in for x? Is there anything I can't square and subtract 4 from? No. So for this quadratic function, I actually don't have a problem. The domain of t would be all real numbers. If I look at plugging in function t into function r then, so this would be like saying r of, okay, well, t of x is x squared minus 4. So I'm going to take function t, so x squared minus 4, and I'm going to plug it in to function r. So if I take r of x squared minus 4, I should get 1 over x squared minus 4. So I'm going to replace the denominator there with x squared minus 4. And this is my composite function. So, okay, originally I didn't have any problems with function t. Now, you might be thinking, well, okay, if I look at function r, I mean, if I just looked at this by itself, I might be tempted to say, well, x can't equal 0. But careful, for the composite function, if I plug in 0, is 0 okay? Is 0 going to give me out an answer for y? Sure, I can input 0 into the composite function and get out a y value. So I actually really don't need to look at the domain of function r. I want to look at, is there anything that's coming out of the range of function t that causes a problem in function r? Or in other words, I can't have this whole thing equal 0. So since x squared minus 4 is now in the denominator, it's actually, all right, this whole denominator can't equal 0. So this is where the problem is going to come. If I go through and solve, x squared can't equal 4. And if I take the square root, I should put that plus or minus sign out front if I'm solving an equation and I take the square root. So x actually can't equal 2 or negative 2. So let's recap here. This is what I'm looking for when I'm finding the domain of the composite of functions. First off, I want to check the innermost function, the domain of t. I don't have any problems. This is a parabola. I can plug in anything for x. Then I want to check the domain of the composite. So we said, okay, the denominator can't equal 0. So is 0 okay? Because I might be thinking, well, I can't divide by 0. Yes, that's the note we made here. If I plug in 0 first to function t, then, I get something like this. What comes out? I actually get out a real number. So 0 is fine, but what I need to be careful of is what I could plug into function t that will produce 0. And that's where this bottom part comes into play. If I plug in 2, well, 2 squared minus 4 is 0. And if I plug in negative 2, negative 2 squared minus 4 is 0, which is going to cause a problem because I can't input 0 into the denominator. So overall, your domain should be negative infinity to negative 2. -2 to 2, and 2 to infinity. So last example, why don't you give this a try? First, find function h of g of x, so come up with what that would be, and then let's see if you can find the domain of the composite function. So pause the video. So h of j of x, j of x is actually the square root of x, so this is just the square root of x, which means I would want to be inputting the square root of x into function h. Wherever I see an x, I'm going to replace it with the square root of x. So h of j of x actually is equivalent to 1 over the square root of x minus 3. That's your composite function. Now, if I look at the domain, first thing I should be checking is the domain of j of x. So domain of my original function that I'm working with. Are there any domain restrictions for function j? Well, sure there are. If I'm taking the square root, I can't take the square root of a negative number and get out a real number. So x has to be anything greater than or equal to 0. So right away, if I'm just looking at my original function, can't input any negative values for x. I'm going to run into problems if I do that. Now I want to check the domain of the composite function. So the domain of the whole thing, which is what we came up with right here. So the domain of h of j of x, domain of the composite. Well, are there any additional problems? Well, sure. I mean, now I have a fraction. So if I'm looking, well, the denominator can't equal 0. So if I'm just looking at function h, you might think, okay, well, x can't be 3. No, I actually want to look at what values would I input into function j that would give me out 3 that would cause a problem when I plug them into function h. So really I'm looking at this denominator right here, that square root of x minus 3 cannot equal 0. If you go through and solve, the square root of x cannot equal 3. And then if we square each side, x actually can't equal 9. So in summary, if you read my little note off to the right in orange, can I plug in 3 to function j, and then what comes out I plug into function h? Yes, 3 actually doesn't cause a problem. I do get out a real number. The thing that causes a problem is 9. If I plug in 9, the square root of 9 is 3. 3 minus 3 is 0. That's going to produce a problem. So if I combine these two ideas right here, I can only have positive numbers and 0. So the smallest number I could input into the composite function is 0. And then I can input any positive number except 9 is going to cause me a problem, because that would make the denominator of the composite function 0, and you can't divide by 0. So overall, here is your domain of the composite function.